we're now going to take a specific look at the different types of intermolecular forces of attraction. A reminder that there are 4 of them that you need to be familiar with, and in order of increasing strength, dispersion IFAs are the weakest, followed by Dipole Dipole IFAs, which are stronger than dispersion IFAs but weaker than hydrogen bonding IFAs. Hydrogen ion bonding IFAs are weaker than ion dipole IFAs, but remember this category of IFAs is limited and is found only in mixtures specifically mixtures that involve water and soluble ionic compounds, also known as salts. I'd like to take a look at the first 2 types of intermolecular forces of attraction listed, and I'm going to go slightly out of order. Although I've listed dispersion IFAs as the weakest, I'm actually going to begin the discussion talking about dipole dipole IFAs because it's just a little simpler to introduce the overall concept looking at dipole dipole IFAs. So let's examine them more closely. Dipole dipole IFAs are electrostatic forces of attraction, and recall that means that positive charge and negative charge attracts. Electrostatic forces of attraction operating between polar molecules. Now, if you recall, another name for a polar molecule is a dipole. These 2 poles on a polar molecule, one which has a partial negative center of charge and the other pole or end having a partially positive center of charge. So literally, when we say dipole dipole IFAs, you could also read this as polar molecule IFAs. And hopefully as soon as you recall the nature of a polar molecule, it's easy to understand the attractive forces that operate. So let's use, for example, HCl, a polar molecule. And if we draw the Lewis dot structure, we can remind ourselves of that. So looking at the Lewis dot structure, examining the bond between hydrogen and chlorine, remembering the electronegativities. Chlorine has an electronegativity of 3, hydrogen has an electronegativity of 2.1, that's a difference of 0.9, which puts this bond squarely in the polar covalent bond range. Chlorine, being the more electronegative atom, has a partial negative charge, and hydrogen a partial positive charge. We can see the molecule is not symmetrical, with chlorine being the center of partial negative charge and hydrogen being the center of partial positive charge. So we're literally looking at 2 poles on this molecule. What happens when one HCl molecule is in close contact with a second HCl molecule? You see that they will align themselves so that the partial negative chlorine end of one HCl molecule is in close contact with the partial positive hydrogen end of a second HCl molecule. And electrostatic forces of attraction are in effect here. And the partial negative end of one HCl molecule will stick to and attach or attract, try to maintain close contact with the partial positive hydrogen end of a second HCl molecule. So there'll be a force of attraction here, which we call a dipole dipole IFA. Notice that this dotted line here, whatever the symbol that's used to represent the dipole dipole IFA, this attraction is weaker than the covalent bonds that hold HCl together as a molecule. So it would be easier to separate these 2 molecules from each other than it would be to try to break the bond holding a single HCl molecule together and separate the atoms of hydrogen and chlorine. It would be much harder to break the molecule apart from within than it would be to separate the 2 HCl molecules from each other. So again, a reminder here that intermolecular forces of attraction, although significant, are much weaker relative to the ionic and covalent bonds that operate to hold molecules and compounds together. Right, so here's an illustration of dipole-dipole IFAs. This same type of intermolecular force of attraction would be operating between all polar molecules. And note that the strength of the dipole-dipole IFA increases with the increasing amount of partial negative and partial positive charge on the atoms that make the polar molecule. So the greater the polarity of the molecule, the greater its dipole moment, the greater the magnitude of partial negative and partial positive charge, as predicted by the difference in electronegativities of the atoms, the greater the attraction holding them together. So we would predict that HCl has larger or stronger dipole-dipole moments than, say, HBr, because chlorine as a halogen is more electronegative than bromine is. So it would have a greater partial negative charge on the chlorine, greater attraction to the partial positive hydrogen on a second molecule. I'm going to skip this discussion here for an instant. We're going to come back, or for a moment, because we're trying to compare dipole-dipole and dispersion IFAs, and I need to first introduce you to dispersion IFAs. Then we'll come back and take a look at this section right here. So now that we've taken a look at dipole-dipole IFAs, let's go back and take a look at the weakest of the intermolecular forces of attraction, dispersion IFAs. Dispersion IFAs are electrostatic forces of attraction operating between all molecules, polar and nonpolar. However, it is the strongest or primary intermolecular force of attraction found in nonpolar molecules. So essentially, nonpolar molecules, dispersion IFAs are the only game in town for them, the only significant intermolecular force of attraction that exists. If a molecule is a polar molecule, it can have both dispersion and dipole-dipole IFAs, but the dipole-dipole IFAs would be stronger in magnitude for that molecule than its dispersion IFAs. So let's take a look, and I'm using just a general X example for a nonpolar molecule. So X just represents any nonpolar molecule. So here I've drawn a molecule, nonpolar, X, and I'm trying to illustrate what we refer to as an instantaneous dipole, which is also known as a temporary dipole. And what are we talking about here with an instantaneous or temporary dipole? We're talking about a situation where the electron cloud in the nonpolar molecule is for an instant unevenly distributed over the molecule, sort of like laundry in a washing machine that gets unevenly distributed, and then when the machine starts to spin, there's this terrible racket and clanking sound because the clothes are not properly distributed and balanced, so the machine can't spin properly. Well, if you're looking at an electron cloud and it is not evenly distributed, what do you expect to see? Well, you'd expect to see that there's more electron density on one end of the molecule than there is on the other. And that's what I'm trying to show here. I'm trying to show with this first nonpolar molecule X that the electron cloud has been unevenly distributed and there's a buildup of electron density on this end of the molecule, hence these multiple negative signs, meaning more electron density here. The whole cloud has been displaced to the right end of this molecule, which means that there's less electron covering the nucleus or the nuclei of this nonpolar molecule, and this positive set of charges means that there's more exposure of the nucleus and the positive charge there because the electron cloud has been displaced to the right end of the molecule. This is what we mean by a temporary dipole, and notice it exists only for an instant, for a moment. Unlike the permanent dipoles that we see in HCl and other polar molecules, where the chlorine end of the molecule is always partially negative. It's a permanent partial negative charge on this end of the molecule. With dispersion IFAs and nonpolar molecules, you do not have any permanent dipoles. Instead, you just have these momentary, instantaneous displacement of electron clouds. Well, if this first nonpolar molecule X has more electron density on this right end of the molecule, what will that do to a second nonpolar molecule X that is in close contact? Well, we know that like charge and like charge repels. So we would anticipate that the electron cloud would be shoved aside in the second nonpolar X molecule because of the buildup of electron density on this end of the first molecule. So we're going to see electrons being displaced in the second molecule. So that means we have a buildup of electron density here and an exposure of the partial positive charge of the nuclei on this left end of the molecule. And now we see where the electrostatic attraction is happening. We have a buildup of partial negative charge on this one nonpolar molecule X, and then exposure of the nucleus created by the induced dipole. This instantaneous dipole causes or creates a second momentary dipole on this second X molecule, exposing the nucleus and the positive charge, and we see the attraction that can exist right here between these two nonpolar X molecules. This dispersion IFA happening right here, causing these two molecules to stick or attract together weakly just for an instant, just for a moment. And then the picture changes. The electrons can be redistributed. You no longer have this momentary instantaneous dipole. And if I drew more X molecules here, and let's just draw them in, multiple X molecules, obviously not to scale, you see a picture where you have momentary points of attraction here and here and here and here, but then it can change, and in an instant the attractions are here or here or here or here. So you have this multiple rapidly shifting points of attraction as instantaneous dipoles form, induced dipoles on a nearby molecule, but then the whole picture changes and starts all over again in another point of contact in this entire sample of X. So that's the idea behind how dispersion IFAs work. Note that dispersion IFAs increase as the size of atoms increase. And of course, the bigger the atom, the larger its mm, meaning molar mass. So dispersion IFAs increase as the size of atoms and their molar masses increase. And why is this? Well, the bigger the atom, the larger its electron cloud, and the less tightly held that electron cloud is by the nucleus. Therefore, it's easier to displace the electron clouds of larger atoms and cause temporary or instantaneous dipoles to form, or to induce a dipole on a second nonpolar molecule. So, taking this point and then illustrating it, would we predict that elemental chlorine or elemental iodine would have a higher boiling point? Now we can use the periodic table, right, to help us with this. If the periodic table is color-coded to show solid, liquid, and gaseous states, we know that chlorine is a gas at room temperature, but iodine is a solid. So we can use that clue to help us understand what must be going on with boiling points. Obviously, iodine has to have a higher BP than chlorine. All right, so maybe just say it like this. Boiling point of iodine has to be greater than the boiling point of chlorine because iodine is a solid at room temperature, but chlorine is already a gas at room temperature. So we can predict that from the periodic table, but let's see whether that makes sense with what we've just said here. Iodine atoms are larger in size than chlorine atoms. So both of these molecules are nonpolar, of course. All right, same atoms bonding together, can't have polar covalent bonds, can't have partial charges. So they're both nonpolar molecules, but because iodine is a larger atom and I2 has a larger molar mass, we would predict that it would be easier to create an instantaneous dipole within iodine molecules. Therefore, dispersion IFAs should be stronger in iodine. They are more tightly held together as molecules, causing iodine to have a higher boiling point than chlorine. So our discussion of dispersion IFAs and our notes about increasing size of atoms correlate with the boiling point comparison between chlorine and iodine.